So our next talk will be by Oliver.Gunasekara. He's a co-founder and president and CEO of NGCodec. He has 20 years of mobile experience, have been responsible for ARM's mobile activities starting in '95. He spent 12 years with ARM, serving as a VP for corporate business development and mergers and acquisitions until 2007. Prior to co-founding NGCodec in 2012, he was a business development consultant to a number of mobile startups in the OS, security, imaging, and battery areas. Oliver, yours.
Okay, so good afternoon. I think we're almost at the end, appreciate having the opportunity to talk to you a bit about a hardware implementation. So we're a startup. We've been working for about 2 years now on our H.265 hardware encoder. So very quick background of the company. We were founded in 2012. We're very much focused on hardware versus software. And software, as we've heard, can deliver great performance, but it needs a lot of resources. And you'll see in my slide, immense amount of resources. And so we think in a longer term, doing something in software is not as efficient as offloading to hardware, although that takes a bit of time. Our team is a little bit unique in the fact that we work both in FPGAs, where we load a design in, also to traditional ASICs. And we offer the IP for both. So, as I said, our strategy is to really deliver this as an IP core, a bit like ARM, if you're familiar with ARM, and that would then get implemented either in an FPGA, and that would be really for professional markets like video conferencing, or later in an IP core that would get integrated into a system on chip, say a smartphone, which is more for the consumer markets. So, a lot of people kind of say, well, why UHD or why 4K? And in our view, 4K alone is not sufficient. We think many consumers that will sit a long distance from the display, and the display isn't so massive, will struggle to see the difference. That is the reality when broadcasts do testing. You know, to see the difference, you need a big display, and you need to sit not too far away from it. Then you will see the difference. But if you package a number of technologies together under the banner of Ultra HD, I believe it will become very compelling to the consumer. So resolution is only one of those components. We have things like a wider color gamut, the ability to display colors that are normally outside of the range of today's displays. A classic example is strawberries. If you try and look at strawberries on almost any display, any TV display, their color will not be correct because the red of strawberries is outside the gamma of traditional TVs, which can only display about 1/3 of the colors that we're used to. So that is one of the characteristics. The next is really high dynamic range and high brightness. And so we're seeing displays move up from 100 nit displays, which is what was the norm in CRTs, to 1,000 nits, which is a much brighter experience. And again, once you do that, you have a much wider dynamic range, and you can show a lot more information in both shadow areas and brightness information. To make this technology work in a display, you typically need a localized dimming. You need the ability to control the backlight in a far more localized area than just at the borders. And the newer displays are doing that. And again, the image quality is dramatically better. Coupled with these technologies is the need for more bit depths, because if we have wider amount of colors and we have wider range, then we need more levels to represent each color, more than the 8-bit or 256. And so we need to move to 10 bits. If we don't, we'll start to see banding artifacts. And so most of the content that is being offered for 4K is also doing 10 bits. And then finally, higher frame rate. Not really for this market, but if you're watching a sports match, if you could see it at 60 frames or 120 frames, it will look more lifelike, more crisp than if it was being displayed at 30 or 60. And so I think what's going to happen to the consumer is that all of these technologies are going to be packaged together as an Ultra HD experience. And in parallel, I think the content, Hollywood, is going to master the content for this, assuming a brighter display, assuming HDR, and assuming a wider gamut and a higher bit depth. And that together is going to be the next experience for Hollywood and movies. And that is, I think, what is going to make UHD successful. If you want more info, I just wrote a blog post on this about my next TV, which I hope may be an Apple TV that provides all of this technology. So we've all heard about the new codec. I think everyone knows the promise, and the presentation before shows that it actually can deliver. We can half the bit rate for subjective analysis over the previous generation, and that's a significant achievement. But there is a challenge, and that challenge is the fact that it's very hard to implement. There is so much more complexity now in this codec versus the previous codec that you need many more cycles. So if we talk about the interprediction, it's got a lot more sophisticated. We talk about intra, we now have 33 directions versus the 8 directions that we had in 264. The RDO has got immensely sophisticated because of all of the different modes that one can choose to use. And so it is becoming very, very challenging to deliver the performance without needing supercomputers if you do it in software. So what our approach is to really offload the software to an accelerator. And that accelerator in our first instance is something like an FPGA design. Because if you look at this graph here, you're seeing that what today is maybe 21 watts to encode HD at high quality, once you go to the new codec, that goes up about 10x in power consumption on an Intel platform. But that's just for 1080p. As soon as you now want to go from 1080p to 4K, we go up to about 1.3 kilowatts, about a 64 times increase. And this will translate to cost and power. And that's the real pain that we see of the new codec. Our approach is to offload that to a little FPGA chip that we get from Xilinx. It's state-of-the-art chips. Every year they come out with new ones. Today they have 20 nanometer chips. And by writing our algorithms to run on that FPGA and designing our hardware that implements the codecs precisely as we need, we can lower the power consumption down to about 20 watts from that 1.3 kilowatts. And obviously, later on, we can go to an ASIC if we need to and get it down to maybe 1 watt. This is the beauty of hardware. We get all of that efficiency, but we don't give up the performance. And this is why we feel an FPGA is a really good approach to a lot of products. Something else I want to talk about, we announced a partnership and a demo with a company called Apical. So Apical is an IP company that does some imaging technology, ISP and analytics. And they have an engine that can analyze a video scene in real time and detect the people. And so what we did in the demo that we put together was that we used their engine as a preprocessor for our encoder. And what they did is they identified the regions of interest, i.e. where the people were in the scene. And we used that information as part of the rate control of our encoder to prioritize the quality where the people were and have ideally a very, very low overall bit rate, but yet have very great quality on the people, because that's what people care about. And so the end result is what I'm showing here. So you've got an image here on your left, which is high quality everywhere. And you can see that, the projector doesn't do it justice, but it's pretty decent quality, but it's 5.3 megabits. So what we've done by analyzing where the faces are and only using the high quality on the faces, we now get this bit rate down to 1.5, but for the faces, we still have the high quality. And so this is a form of region of interest encoding. And this can run in real time because their encoder, their analytics engine is a hardware block that runs in an FPGA just like us. And so the one talks to the other. And it's a great way of reducing the bit rate whilst preserving the perceptual quality. Okay, now I'm going to talk a little bit more about the specifics of our implementation. So we are building a generic encoder that can actually serve a range of markets. And someone that is building a broadcast encoder is different to someone that's building a unified communications encoder. But we want to make sure our design can scale. And so what we do is we have the ability to define certain compression capabilities. And you can see the graph on the right. And what we're showing here is different performance bars. So with the one in red, we're showing that we need approximately 12% more bits than the HM to achieve the same quality as measured on PSNR. So it's not as good as the HM, but it needs much less resources. The one in the middle, which is what we call the base, needs 8% more bits. But the one on the green needs only 5% more bits. Now, achieving the HM quality, as was showed previously, is very challenging because the HM model is brute force. What it does is it tries everything in the standard, tries it all, and then sees what works and puts that into the bit stream. Any real-time encoder in software or in hardware cannot do that. It has to take shortcuts. And it's the art of the encoder vendor to design algorithms that approximate the same performance as the brute force, but with maybe 2 orders of magnitude less complexity. And that's what we do. Now, we don't quite get there. That's why we need a few more bits, a few more, 5% or so more bits, but we get very close. But the differences between each of these is about 3x in resources or silicon area or FPGA. So basically, you go up 3 times in size and 3 times in cost of the chip that you buy just to get those few extra percent. So it makes a big difference, and that's why we have to design our IP to scale, because people that want ultra-low power don't want to spend all of the money for the one that is very, very high performance. And also, the power consumption would be really, really high. The other thing to mention is that we are using a technique in the standard called WPP. So WPP is a tool called wavefront parallel processing. It's part of the standard, and it's a technique to parallelize the encoding. But unlike the precursor tiles, where you break the region into different regions, what we do is we work on a wavefront. And it has the nice advantage of not losing a lot of compression efficiency. And we also don't have the potential artifacts at the boundaries of the tiles. But it needs more memory. But it does mean that by putting 4 of our engines together, we can do a 4K design. In fact, if we need to, we can put more engines and scale all the way up to 8K. Again, we can do that scaling in one design or discretely by using the discrete SerDes connections on FPGAs. A little bit more about our design. We took the decision to include a lot of microprocessors inside the design. These microprocessors are effectively state machines, and they're tiny. They're of the order of 10K gates, so noise in what is a multi-million gate design. But they give us an awful lot of flexibility. They mean that we can modify things like the mode decision, the rate control, the RDO in real time. And in the past, what we did is we hand-coded some of these as state machines. Now, by moving them to software, we have a lot more flexibility. So even though it's a hardware design, it can be significantly modified by changing the C firmware that runs on the design. In an FPGA, these are microblaze cores. In an ASIC, these are tiny little tensilica cores. But it gives us a lot of flexibility to optimize and tweak the encoder for different scenarios, different types of applications. And let's give some results. So, you know, we've been working on this for a little while now, and if we take the Intra side, we have now achieved with our own algorithm performance that is almost identical to the HM, but we're using something like 1,000 times less resources. So our team has developed an algorithm that's much, much simpler than the HM, but yet performs almost identical, hence the two graphs are the same. And this is for one of the most complex sequences. I think it was the basketball run sequence, if you're familiar with the standard. And so that's a great result. And now we're working on some of the other blocks. So it's the fact that we have a team that has done video codecs for many, many years, and many of them were actually involved in the standardization in the JCTVC. So my last slide really is that, you know, there are HEVC encoders becoming available. There are many software encoders, and some of them are performing quite well, but they are needing immense amount of computing resources. And we think in time, a hardware solution is the right way, either with an FPGA, with an accelerator card for a server, or via an IP core that would get integrated. And we also think that, you know, things like higher dynamic range, wider gamut are also going to be very important for 4K. And so whenever you're considering 4K, I would argue to think beyond resolution and think about the total image experience that can deliver. Okay, thank you very much.
Thank you. By the way, speaking of ultra high definition, Apple today introduced a new iMac, and it has a 5K display. Have a look at the details, but it must be an impressive piece of hardware. But it's certainly indicative of where things are going. So questions for Oliver?
And the PDF of the slides are actually on this URL, if you would like them.
So is this deployed commercially, or is it still in the development phase?
We're still in the development phase.
Okay.
You know, next year will be widely, well, we hope to release the encoder. It's, you know, our project is about a 20-man-year project, and we're a good way through it, but not yet at the end.
And the deliverable will be the IP, right? So it will be embeddable on people's designs.
Yeah, so yeah. IP that you can put inside an FPGA, or IP that you can put inside your chip.
Yes.
What I would say is we're also thinking about offering an encoding service ourselves.
Okay.
So that would be a cloud-based API service that you could use.
Russell has a question.
That area of interesting is a neat trick, but you can think of plenty of situations whereby the face is probably the least interesting thing. How can you optimize that to make sure that the most interesting thing is getting the most resolution, which may not be a face?
It's very tough. I mean, to be honest, that's not our area of expertise. It's a third-party company, Apical, that creates that engine. I know it's a programmable engine, but you have to ahead of time tell it what you want to track. I would say in many use cases, the faces are. You know, as humans, we're just programmed to zoom in on faces and record detail there. So I think as a first pass, that's good. But if you could somehow infer, that would be great.
Well, the scenario that I thought of was probably the most extreme case is a sports broadcast, right? Where the faces in the crowd are the least interesting thing, and the most interesting thing is the ball, right? So there are many different permutations on that general concept.
Yeah, absolutely.
If I may add to that, there has been a lot of research on sort of scene detection algorithms on video dating back to, I don't know, 20, 30 years. And I can certainly imagine right now your camera has settings for shooting like still images, right? And you can specify like the scene type. It's like a sunset or is it a close-up? So I can certainly imagine situations where different algorithms are loaded depending on the situation. So if it's a sports scene, it's tuned not to find people, but to find like fast-moving blobs. Right? Yeah. So yeah. Other question? No? Thank you very much, Oliver.
Hey,
thank you.
Thank you.